Let's get started. So we are continuing with the eraser is gone again. Okay. It's got to be here. We're going to continue with equations. We already looked at what an equation is, how to solve linear equations, how to solve quadratic equations, how to solve equations with radicals, and how to solve absolute value equations. So now we're going to talk about solving a couple other kinds of equations. In particular, I want to talk about right now equations with rational expressions. So we're still in 1.5 equations. The next one is equations with rational expressions. And we know what a rational expression is. We defined that before, not going to redo it. But basically here, the strategy to multiply through by the LCD and then use a previous strategy. So in the same way that when it came to dealing with equations that had radicals in them, basically we isolate the radicals, raise both sides to powers, and ultimately after we do this for a while, we get an equation that's more normal, where it doesn't have anything weird to deal with. That's the same kind of idea here. So rational expressions, when you have a division of expressions, and find the LCD, multiplying through will kill all the denominators, so now you don't have fractional rational expressions anymore. And you'll use the previous strategy, so it might be linear after you multiply through, might be a quadratic, might be something else that you have to factor to solve. And again, in this case, it's also very important again that you check your answers. Because every now and then, you'll have an answer where if you plugged it into the original, it wouldn't work. So for example, because it's rational, the denominator, you can't plug in any value where the denominator is 0. But those guys might show up as answers here. And at that point, after checking it with the original, you know, oh, I can't do that. So basically 3 steps here. And we've actually been doing similar manipulations. So at this point, let's just get through some examples. And write them down over here. Example. X over 3 plus 1 equals 2 over 5. A, B. 1 over 2 is equal to minus 3 over x squared minus 10. C. X over x minus 2 plus 2/3 is equal to 2 over x minus 2. So this guy and anyone similar to this guy, it has rational expressions, it has divisions. Right? So that tells you whenever you see that and it's an equation, which means there's an equal sign. If you want to solve for x, you would first multiply through by the LCD to get rid of the rational expressions. Simplify it and it will look like a previous kind of equation that was mentioned earlier in this chapter, and then solve it using a previous strategy, and then check your answers. A is not so bad to start out with, so x over 3 plus 1 equals 2 over 5. This is a linear equation, and you could actually do the linear strategy right away, but dealing with fractions, I think, can be detrimental. So what you would first do is to multiply by the LCD so you don't have to work with a lot of fractions. And in this case, the LCD is what? 15. So you're actually going to multiply the entire equation by 15, which means the distributive law would apply. So 15 will multiply everybody. Multiply the first guy by 15, what's going to happen? You'll end up with 5x because the 3 would cancel into the 15, leaving you with 5, and you end up with 5 times x, plus 1 times 15 equals here, the 5s would cancel, you'll end up with a 3 times the 2 would be 6. So now it's a linear equation, and you only have integers, so it's a bit easier to deal with. So again, the idea here is to isolate the x. We subtract 15 from both sides. So subtracting 15 there gives us what? Minus 9. And so now we get x would be minus 9 over 5. And you can check this. I'm not going to do it here because this is linear. The denominators are all constants, so 9 over 5 seems perfectly reasonable to me. Let's look at B. We can talk about an alternative here, which ultimately does the same thing. If you have two fractions, you can do something what you call cross multiply. It's essentially like a nicer way of multiplying both sides by the LCD. However, it only works in the simple case where you have one expression and the other one. So we could do something here called cross multiply. What that means is you would multiply by this guy and multiply by that guy, which creates a cross. And it's a nicer version of the LCD strategy if you have only one term on each side. We call this cross multiply. So you take the x squared minus 10, multiply by 1, that will give you x squared minus 10, equals, take the 2, multiply by the minus 3, that will give you minus 6. So ultimately, you can bring this guy over, you get x squared minus 4 equals 0. That is a quadratic, so we try to apply the factoring strategy first. If that doesn't work, we use quadratic formula, but in this case it does work. This is the difference of squares. And so we get x equals 2, x equals minus 2. And again, you should check. But I leave it to you to verify that those actually work. So for example, whether you plug in plus or minus 2 into the square here, it will give you a positive 4. And if you take positive 4 minus 10, that will give you a negative 6. Negative 6 divided by negative 3 divided by negative 6 is actually positive 1/2. So that actually works out. I also want to show you here if you were to do the strategy of multiplying by the LCD in this case would be 2 times x squared minus 10. Multiplying out here, the 2's would cancel, and you'd be left with x squared minus 10. Multiplying here, the x squared minus 10's would cancel, you'd end up multiplying by 2, and you get exactly the same thing. Right? It's the same idea. Some people just might find it easier to think about cross multiply. But the strategy of multiplying through by the LCD is going to work. It's the general version, it's the general case. It's probably the one, if you have to remember one technique, remember this. It'll cover the cross multiplying case. Let's look at this one. Let's see. X over x minus 2 plus 2/3 over x minus 2. What is the LCD here?
3 times x minus 2.
Right, 3 times x minus 2 is the LCD, so I'm going to multiply the entire equation by 3 times x minus 2. Again, distributive law, so I'm going to multiply this, multiply that, multiply this. In the first case, the x minus 2's would cancel, so I end up multiplying by 3, so I end up with 3x in the first position, plus. In the second case, the 3's would cancel, so I have the 2 multiplied by x minus 2. In the last case, the x minus 2's would cancel, so I end up having the 2 times the 3. So I now have this equation. This equation is linear, even though it's not in its most convenient form at the moment, so at this point, I'll start to expand parentheses, and so this would be 5x equals, bring this over here, is 10, right? And then I would divide both sides by 5. Okay, and is that the answer?
No solution.
No solution, because in the event our x is 2, we divide by 0. So here you'd realize, so this is an important one to check. This is not the answer, because to check in original, if we plug in x equals 2, we would end up with 2 over 2 minus 2 plus 2/3 over 2 minus 2 minus 2, and this guy here is division by 0. So ultimately, for us, we would say this has no solution, and that is the correct answer. So the correct answer here is no solution. Right. The only possible candidate for the solution is 2, but that gives us a division by 0. And so that's why in this method and with radicals, it is important to check your answer. This step is actually a very important step. Pretty much all we have to cover on the. Another definition to wrap up this section is just to talk about things called identities. I don't know if I want to say equations with no solutions, or I probably refer to these guys as contradictions or something like that. And we'll even talk about trig identities in this class, but that's a very popular kind of identities. But identities is a more general term. So an identity, this is an equation that is true for every input, or every permissible input, right? Obviously, if there's something that will stop you from plugging in a certain value, that's not permitted. This is called an identity. Okay? So for an example, there's nothing really to solve here. It's just a matter of just knowing when these guys show up. For example, 8x plus 12 equals times 2x plus 3 is an identity. Okay. Now, what happens when you get an identity, how you know something is an identity, how you would actually show something is an identity, is notice that if we try to solve, it will ultimately be a fruitless effort, but not as fruitless as it could possibly be. You would get something like 8x plus 12. On this side, you multiply out to get 8x plus 12. Then you'd be like, okay, let's isolate all the x's. But then when you subtract 8x from both sides, that's gone. Subtract 12 from both sides, that's gone. You'll end up with an equation like 0 equals 0. Okay? So whenever you're solving an equation, you end up with something like that. First of all, make sure you check your work and you actually did everything correctly, and you end up with, when you end up with this scenario, you know that's the right scenario. But what that scenario means is that the equation in question was always true. It's true for every value of x. So what you get is you get a statement that is literally, of course 0 is equal to 0. That's always going to be the case, right? And so basically you will say it's true for every x. Right? So there is no statement in the end that says your x has to be this. No, your x could be anything. And that ends up being an equation where no matter what you plug in for x, it is going to be true. So this is what's called such an equation. This is a very super obvious case. The two sides can look very different, but ultimately they simplify to the same thing, and such equations are called identities. Sometimes it's not obvious and we want to prove that one side is exactly the same as the other side, and trig identities is a very fun place to actually do that. But this is what an identity is called. So identity equations are, they happen to be very useful because they might indicate relationships between two different expressions or functions that were perhaps thought to be different in the beginning, but by realizing that an identity equation shows up when you compare them, we'll show you that, no, these guys are actually exactly the same thing. Conversely, so an identity is something that's always true for every x value. You can have the opposite effect, something that's never true for any x values. So a contradiction. It's an equation that is always false. It is never true for any input. Another stupid example here, where someone tells you, okay, 2x plus 1 equals 2 times x plus 3. This would be an example of a contradiction. Because if you try to solve this, 2x plus 1 equals 2x plus 6. Subtract 2 from x from both sides. What you end up with is 1 equals 6. Now, that is obviously crazy. Right? That is never going to be true. 1 is never going to be 6. These are two different points on the number line. And so this is called a contradiction. And this means this is an equation, no matter what x you plug in, it's never going to work. Because for that equation to work means 1 is equal to 6. Right? So no x will make this true. Right? Even when I'm allowed to plug x's into each side, which they're polynomials, I am allowed to plug in x equal to each side. It's not like there's a division by 0 or anything to worry about. These are perfectly nice functions that I can plug in a bunch of things into, but none of them will actually work. The difference between this and the very last example I just showed you, where we saw that we said it's no solution, I wouldn't call that equation a contradiction because x equals 2 wasn't a permissible value in the first place. So it's not like everything I plug in here is never going to work. It's just that the one thing I'm allowed to plug in, the one thing I'd like to plug in wasn't allowed. But this is a very different situation. And again, this can also indicate the relationship between two functions. We can know two functions will never be the same. They'll never actually intersect or interact. And that can help us solving certain problems. So those are just two kinds of equations for you to know exist. And that kind of ends the equation chapter. So that's the end of 1.5. We are now going to move on to 1.8. So 1.6 is complex numbers, so we're skipping that, that's not in our syllabus. 1.7 is, I think it would be good if it was in our syllabus, but it's not. It's something that teaches you how to set up word problems. If you're given word problems, how to set up equations from them. More of an applications-based thing, but we're also skipping that. And the next section to talk about is 1.8, in which case we deal with inequalities. Now, this is going to be also kind of quick because we have looked at inequalities before in this class when we were looking at domains. So for the most part, this is kind of also going to go very quickly. But I just want to make sure we're all aware of all the rules that come into play when you're doing inequalities. So we are skipping to 1.8. Inequalities. So these are different from equations in the following way. That's basically an inequality. Basically, we're comparing two statements, and the point is to say they're not the same. We do have reason to believe that one is bigger than the other, or one is smaller than the other, or they're possibly the same, but this is probably not known at the moment. So one could be bigger than or the same as the other, or one can be smaller than or the same as the other, right? So it's when you're comparing two quantities, but you really want to make a distinction between the two. They're not the same. An equation is a statement that says these two are the same thing. Inequality is it's a weaker statement. It's kind of, one might be bigger than the other, or we know one is definitely bigger than the other. Okay? So when you want to make that kind of statement, the mathematical abstraction of that is called an inequality, right? So it's not an equality, it's an inequality. Okay? So we have symbols. Symbols here, and their meaning when read from left to right. So we have this guy, this guy, this guy, and this guy. This symbol means greater than. This means greater than or equal to. This means less than. This means less than or equal to. Okay, so for example, I can say x is less than 2. This is the same as x is less than 2. Okay? So if I'm reading from left to right, this symbol would be read less than. Now, everything comes down to a relationship. Saying x is less than 2 is actually equivalent to saying 2 is greater than x. Right? In which case you could write it this way. So inequalities can be flipped, and in terms of the way they're read, you read them from left to right in that way. But someone seeing this, they can say x is less than 2 or 2 is greater than x, and they'll be correct. Okay? It's just that when you're reading it from left to right on a page, this is the way it should be read. Probably a better way to think of it, just to think more abstractly, is to kind of think of Pac-Man. So remember, Pac-Man is that head, right? He always wants to eat the bigger guy. Mouth opens towards the larger term. Always. Right, so you can kind of think of the symbol in that way. So when you see something like a symbol like this, right? So if your x is on this side and your 2 is on that side, the Pac-Man is going for the bigger guy. The 2 would be larger. Versus if the x is on this side and the 2 is on that side, this is the statement that x is larger. Right? You always want to chomp the bigger guy. So you can always, every time you read one of these symbols, look who the mouth is opening to, that's the bigger one. Okay. But right from left to right, that's how you read them. But the idea is, this symbol is identifying the person who could possibly be larger. Conversely, you can think of it as the person who would possibly be smaller. So this statement states that 2 is larger than x and x is smaller than 2. Okay, now when it comes to solving equations, inequalities. So again, this is finding all the x values that make the statement true. Very similar to equations. It's just that for this, usually you won't have isolated values that make this true. You'd have a whole bunch, a range of values that makes this true, and even infinite number of values. So solving inequality, this means finding the inputs that make the statement true. So making the statement that x plus 2 is larger than 3, the x's for which this work this would actually work for all x values larger than 1. Right? As long as your x is larger than 1, adding 2 to it will give you something larger than 3. And so one way to say this is to use the interval notation. And so this would mean you could say your x is 1 or bigger. So we've looked at interval notation before. So that would be the solution. Okay? Now, this might be obvious. It's not always as obvious what the answer is. So we have to come up with some sort of strategy for determining if our inequality happened to be more complicated than that, how would we go about finding the answer? Right? But this is what it means to find the answer. Tell me all the x values that makes the statement true. This statement would be true for all x values larger than 1. Now, how you go about finding those things to be true, that's the important part. So now let's talk about the strategies for solving inequalities. So here is the idea 1. And this is going to have a caveat on it, which I will give you at the end of the strategy. You treat the inequality as if it was an equation. So someone tells you this statement, for a brief second you just pretend that was an equal sign. 2, there are some ways in which this can be different, which I'm going to say next. 2 is to solve the equation. Okay. Using what we learned from the previous section. 3. Now comes the part that we've done before. You are going to test the intervals created by the above solutions to see which makes the original inequality true. Right? Those will be that will be the solution to your inequality. Here's the star. So we have caveats here. So for the most part, we can treat it exactly like it's an equation when finding these x values. There are some key differences, though, between inequalities and equations. If in order to solve the equation, if you have to multiply or divide by a negative number, you must turn the sign around. Okay? So that's the first difference. So if we have something like, example, if you see something like minus x is bigger than 3, and you want to be able to talk about what are the x values, treating that as an equation, you would obviously want to divide both sides by -1 or multiply by -1, as the case may be. When you actually do that and you multiply by a negative, right? Once you go like, okay, to talk about x, I'd multiply by a negative to make this just x, and I'd multiply that by a negative. The resulting thing must have the sign flipped the other way. Okay? So this has to be something that happens while you're doing that. So in that sense, an equal sign, the direction, there is no direction in which it points. But when it comes to an inequality, it differs from an equal sign in this way, that if you multiply or divide by a negative number, you must change the sign, turn the sign around. So to say that negative x is larger than 3 means that x itself is less than negative 3. Right, and this kind of makes sense as well if you even think of it in terms of numbers. If you say 2 is less than 3, then if you take the negatives of both of them, the sign actually has to turn around. The -2 is actually larger than -3. Right? If you look on the number sign, the positions of these guys, you will realize that the symbols have to turn around. Okay? Because on the number line, this Pac-Man symbol is literally always telling you the guy I'm trying to eat is on the right of the other guy on the number line. So you'll notice that 3 is on the right of +2, but the relationship flips on the other side of the number line. The guy that has the 3 is on the left of the -2. So multiplying by a negative flips the script. You have to turn that sign around. So that's one way in which an inequality will differ from an equation. There's another way in which an inequality differs from an equation. In the sense that there is another maneuver for which you have to turn the sign around. Does anyone know what it is? This is often a forgotten part of the rule. This only really applies if both are on the same side of 0. Okay? Now, if you know that both are on the same side of 0, this will have to be this is the rule. You must turn the sign around if taking reciprocals. So, for example, if you know that x is less than 3, but at the same time you know they're both positive, so they're both on the right side of 0, then it means if you put 1 over x and 1 over 3, the sign has to turn around. Right? If you think of, you can think of again of a key example with specific numbers. To say that 2 is less than 3, it must be that a half must be bigger than a third, and obviously that's true. Right? So if you take a reciprocal, you have to turn the sign around, as long as they're on the same side of 0. If they are on opposite sides of 0, the original symbol stays. Right? For example, -1 is less than 2. Now if I decide to flip both sides, the left side will still be a negative, and the right side is still going to be a positive. A negative number is always less than a positive number. Taking reciprocals here would not actually turn the sign around. It will stay the same, because one side is always positive, the other side is always negative. However, if they are on the same side of 0, both are negative or both are positive, you take a reciprocal, you need to turn the sign around. Okay. That's pretty much it. Other than that, let's actually just jump into some examples now. So essentially, this is the strategy. We're going to treat it as an equation, solve for the x values, but we have this extra step of testing which values work, and the answer usually comes in intervals. You'll have a lot of x values that will solve it. The caveats are, multiplying by or dividing by a negative must turn the sign around. Taking reciprocals, provided both are on the same side of 0, you must turn the sign around. Other than that, you treat it as an equation up until this step, and for the third step, you do the test. Okay, let's do some examples. Solve for x. A squared plus 1 is less than 3. B. Do I want to deal with this one last? Because there's a whole other lesson to deal with absolute values when they're in inequality. Let me move that one last. B. This also has its own lessons, but I'll talk about that when we get to them. And D, absolute value of x minus 1 is less than 2. So we're going to get through these 4, and that'll actually end the section. Pretty much all the lessons I want to teach can be taught by these 4 examples. A. So here that 2x plus 1 is less than 3.
Minus 1.
What you can do is, exactly, pretend it was an equation. It would be a linear equation where you want to isolate the x. You're going to do the same thing here. Subtract 1 from both sides, d2. Then divide both sides by 2.
And then switch.
And so that would be x less than 1. We do not switch because 2 is a positive number. We divide it by a positive number. Now there's not much to check here. This kind of gives us what we want. But you can see here that on the number line, if I were to check something like that's less than 1, like a 0, versus something that's bigger than 1, like a 2, you'd realize that if I plug in 0 into the original, this would be 2 times 0 plus 1, right? That says 1 is less than 3. That is actually a true statement, right? Versus if I plug in something that's on this side of 1 into that, 2 times 2 is 4 plus 1, that's 5. 5 is not less than 3. So it is clear that this side is what gives us the answer. All values that are less than 1 will solve that inequality. Right? So this one is the very easy case. B is already slightly more complicated. However, again, we would start by pretending it's an equal sign. If this were an equal sign, what would you do? Yeah?
Add x on both sides.
Add x on both sides. So you bring everything to one side and make the other side 0. Then what?
Factor.
Factor. That would be the next step. So we have x and x. What does that factor into?
Plus 3.
Plus 3 minus 2. And so now from this you get x equals minus 3 and x equals 2. Okay? Now remember, those are not the values we care about. We care about all such values. So once it's an inequality, once we find that, we now have to test it. So we're going to plot these two guys on a number line. The first thing you want to consider is, do these values themselves solve this inequality? And the answer would be yes, right? If my x is actually minus 3, this will be 0, and that would mean equal to 0. If my x is actually 2, that would make this part 0, and we would be equal to 0. So these values themselves are parts of the answer. So here, we can put a point and we can shade it in. Our x values can actually be equal to these guys. What we don't know is who in these 3 intervals that we've created would also work. So what happens then is we test the interval. So we would simply plug in numbers in each part. Pick a random number, like minus 4, 0, 3, okay? And it does not matter which number you pick, so you just pick the easiest one to work with. The very next integer that's smaller than minus 3, and the very next one that's bigger than that, and 0 is pretty much the easiest guy to work with in that interval. It will work with any number. You could pick 1,327, but why would you? Just pick something that's easy, because it will work with any number. And so what you do is you plug it into the original. A little pro tip here. All right, become a pro. It's nicer to plug into the factored form. So strictly speaking, this is the guy you want to check, but that guy is the same as this guy, and this guy is easier to check because now it's just very small expressions being multiplied together, and it's easier to tell the signs in that case. So if I take a -4, plug into here, that's clearly a negative number. Take a -4, plug into here, that's also clearly a negative number. So here I have negative times a negative. Okay. So that's a positive, which I do want it to be positive. I want it to be greater than or equal to 0. So this side works. Okay. Now, we would have come to the same conclusion by plugging it in here, but here it's harder to check. Because at this point I have to square the 4. Okay, that's 16. Okay, -6. All right, that's 10. Right? And then I compare that to the +4. Right? The computations are actually harder here. It's much easier to check it here. Similarly, I can plug in 0. This will be +3, -2. That's a positive times a negative. That gives me a negative. Negative means it's less than 0. That's false. So that does not work. Do the same thing with 3. Plug in a 3 here, I get a positive number. Plug in a 3 here, I get a positive number. That is positive times a positive. That is greater than 0. So that works. So ultimately now, what works is here and less, or over here and more. The guy in the middle does not work. And so the solution to this inequality will be all x values that are up to -3, including -3 or less, will work. Or you can choose values that are 2, including 2, and larger. So that would be the answer here. And this was something that I also mentioned. This is another pro tip. First of all, you could recognize that y equals x squared plus x minus 6 is a parabola. Now, if you know what the graph of a parabola looks like, it should be obvious to you where the positive sides would be, because the axes, since we already know the answers, let's actually just put this kind of to scale. The axes would come in something like that, where this is going to cut through -3, that would cut through +2. And so you can clearly see the graph is positive on the outer parts, and the middle part is negative. So the professional student looks at that, they'll immediately know that the outsides are what they want without doing any checking whatsoever, because they know what the picture looks like. So we'll talk about graphs in the next section and in future sections, but graphs can really simplify calculations, and it really helps you a lot with intuition. So you could actually look at, sometimes when you get to an inequality, it's actually a familiar expression where once you start thinking about the picture, a lot of things will actually make a lot of sense, and you can actually get away with not doing all the work. So that's something else. So if this thing were flipped, like negative sign, I would immediately know that the middle is now going to give me the answer, because the parabola would shape like this, and it's the middle part that will be bulging above the x-axis. So that's another problem. Any questions so far? I know I'm kind of going fast, but we've actually looked at this since this semester, so I feel like I can go a little faster. Let's talk about C. Now C and D have their own little side issues. And C is probably also an exception that I would add to the exceptions before, how you treat it exactly like an equal sign except for blah. Yeah, something like C would probably be an exception I will add as well. So let me actually specifically state what exception I'm talking about. So here's the thing, here's another way in which you treat this different from an equation. You do not want to clear the denominators. Multiplying through by the LCD is a bad idea when you're talking about inequalities. That's probably somewhere I would think of it's different. So you might think, oh, let's just cross multiply this by that, so now we don't have any denominator anymore. Bad idea. It turns out we always need to know where a division by 0 might happen. The denominator always needs to be in the forefront, because not only do we need to avoid division by 0, but one peculiarity of a lot of functions is on, when you figure out the point where you would divide by 0, on either side of that point, it'll actually change sign. Right? That's a very common occurrence. So when it comes to inequalities where we actually care about the sign of something, clearing the denominator it causes you a loss of information that it can be hard to come back from. Okay? So you always want to have the denominator there, and on your number line, you also want to plot the numbers that make the denominator 0. You just leave an open circle there to tell yourself it can't be that number specifically. But it will be an important point to test. Okay? So how these guys would work is you want to actually keep the fractions around. So you'll start by moving everything to one side, combining into one big fraction, and then you'll set both the numerator and denominator equal to 0 because you need to keep your eyes on both of them. Okay. So if you have a rational expression in an inequality, do not clear the denominators. So what you would do here is instead bring to one side, combine into one big fraction, set both numerator and denominator equal to 0. Find the x's. So that's the strategy. So let's actually see how that would look here. See. What I would do is I would add 1 to both sides. Do not multiply through by the LCD, keep that fraction. Now I want to combine those. We can do that by creating a common denominator. So this 1 I'm going to multiply by 4 plus 5x over 4 plus 5x. And so now I can combine it all under 1 big 4 plus 5x. So that would give me 2 minus 7x plus 4 plus 5x is greater than 0. Now start simplifying the top a little bit. I have 2 plus a 4, that's a 6. Minus 7x minus 5x, that's a minus 2x. Over 4 plus 5x greater than 0. Now what we're going to do is we're going to set the top equals 0, 6 minus 2x, and set the bottom equals 0. So now, what would result from doing that? 6 minus 2x equals 0, this would mean that your x equals 3, right? And if 4 plus 5x equals 0, this would mean that your x is minus 4/5. So we will plot these on a number line. Minus 4/5 and 3. Now immediately I know, because this makes denominator 0. So immediately, right away, I'm going to put an open circle here. I immediately want to know, that's a guy I can't touch no matter what. Okay? Now for the other guy, you determine whether you open a circle, you determine whether to shade it or not based on the original. Now the original is what we call a strict inequality. There is no equal sign, which means being equal to 3 is now illegal. So you'd also leave that unshaded. If there were an equal sign here, like greater than or equal to, you would actually shade that guy. But in this case, they're both unshaded. And again, now you go and you test numbers in between them. So I can test something over here like a -1, and test something over here like a 0, test something over here like a 4. And I'm going to test it into the combined form. Now if I plug in x equals -1, that would give me a positive in the top. Plug in x equals -1 would give me a negative in the bottom. Right? So that means that gives me a negative. Do I want to be negative? No, I want that to be positive, so no. Now I test 0. If I plug it into the numerator up there, that gives me a positive in the top. Plug it into the denominator, that also gives me a positive in the bottom. So yeah, that can work. So in between these is a part of the answer. Now if I plug in a 4, right, so now if I plug in a 4, right, so that's 6 minus 8, so that's a negative in the bottom, in the top, and a positive in the bottom, so that's negative, so here it does not work at all. And so the solution here is only things strictly between -4/5 and 3 are possible solutions. Yeah.
I'm having difficulty understanding why you need them both to be positive.
I don't need them both to be positive.
So-
If I had a negative over a negative, that would also work.
Oh, okay, so, but why does it not work when one is positive and one is negative?
Because it has to work in the original. This says greater than 0 means positive. I need this to be greater than 0. That's the same as saying this is positive. And that's the same as saying I need, when I do this division, to get a positive number. Yeah. So when you're doing that check, you're always checking the original, but this would be nicer, like the simplified version of the original. So you're really only checking what works here. So if the sign was actually turned the other way around, the outer ones would actually be the answer. Now, one other thing I want you to be aware of is what if someone had canceled the denominators and solved for the x value. It turns out that they would only have x equals 3 as a solution, okay? Which means they wouldn't know to plot this in general. And at that point, you realize, here's a mistake that could happen. If they're so lucky to actually pick the 0, they'll get that, oh, it works, and they'd actually shade off everything here. But if they decided to pick something larger, like a -1, they'll say, oh, it doesn't work, and so nothing would work over here. Both of these would be the wrong answer. That's why it's important that you plot the denominator, because the sign, as you see here, changed on the either side of the division by 0. Okay, so ignoring the denominator can actually mess you up on inequalities. So that's actually another important caveat. yeah, treat them like equal signs unless you multiply or divide by a negative. You take a reciprocal, they're both on the same side of 0. Or if you have a rational expression, don't clear the denominators, because it's actually a pretty important part of the piece of information. Now, let's look at D. Any other questions on this one? Now there are general rules that I can say about this one, but let's actually motivate that by actually working through this kind of the long way. So remember how absolute values behave, right? It will output a positive number whether what's inside is positive or negative, okay? So this means the inside can be something that's less than 2 or less than negative 2, and this will still be true. Okay? So when you see this, you have to be aware, because of the absolute value, there are 2 cases. You have to worry about the inside, if the inside is positive, versus you have to worry about, is the inside negative? Now remember the definition of the absolute value. If the inside is positive, the absolute value function will literally do nothing. It will just be like as if the absolute values shouldn't even be there, and you would end up with this inequality. Right? If the inside is negative, what the absolute value function does is take the negative of the negative. And so you would end up with this inequality. Right? So you'll have actually 2 options here. Now, focusing on this one, what we can actually do is multiply both sides by a -1, right? And because I multiply by a negative, I need to flip the sign around. Okay. So what this says is that x minus 1 is less than 2. And what this says is that x minus 1 is greater than minus 2. It turns out both of these statements can be true at the same time, and they actually indicate a certain region. If you look on the number line, you can be, if you're talking about things that are greater than minus 2, it's guys from here to there. Talk about guys that are less than 2, be here to there. Notice that the overlap is in the middle region. In other words, we can say that x minus 1 is between minus 2 and 2. And another way to write this down with a shorthand is to have sort of a double inequality. You can actually say x minus 1 is less than 2, but at the same time, it's greater than minus 2. Now that gives us a general principle when working with absolute values. If you have the absolute value of something is less than a number, it always will break into an equation, into a larger inequality like that. Right, so that's a lesson. And this doesn't have to be x, just think of this as some general expression. If this is less than a number, then you would always be able to move this between the positive and the negative of that number. Right? So from now on, whenever you see an absolute value with a less than sign on the inequality, you can immediately assume it means this. Right? Because when you go through and you break down the two situations, ultimately it comes down to that's what's going on. Right?
So that was the answer to that question on that.
Yeah. We're not completely done. I mean, this is just a small little tangent. This will always happen. Conversely, right? If we turn the sign around, what that means is you're looking for the opposite answer, right? In other words, if you think about this picture, turning the sign around is equivalent to me saying, I want the guys on the outside, not the inside. So right away we can know what something in absolute values is greater than another number, what that would mean. It means that the answer lies on the outer edges, right? And that one would immediately break into two separate inequalities, which I can't really combine them. So that would immediately mean that it either has to be less than minus k, or it has to be greater than k. But again, this one is much nicer. You have one neat little formula. If it flips the other side, just know whatever answer you got here, take the opposite, right? Having less than a number means you're taking the middle. If it means more than a number, you're always taking the outer edges. Now, let's pick up where we left off. So we have x minus 1 less than 2. Your next line, whenever you see something like this, should be that. Right? Now, you don't have to explain where that comes from, because I just told you where that comes from. I'm going to assume from now on you know where it comes from. That's the second line. Okay? So whenever something in absolute value is less than a number, it means you put the positive and negative number at both ends, and that thing is in the middle. Now, this, again, you treat it just like an equation. You can add things to both sides, multiply by both sides, etc. Right? So what we can do is to add 1 to all sides. Right? Because if you treat these as an equation one at a time, that's how you would solve it. Right? So you could just do it all at once across all sides. So this will give us minus 1 over here. This will actually give us 3 over here. So this is to say that your x has to be between minus 1 and 3. Or in interval notation, which is usually what I require you write the answer in, it's between minus 1 and 3. Right, so this on the number line, minus 1, 3, the answer is here. And you can check it. Pick any number between minus 1 and 3. 0. 0 minus 1 is minus 1. Take the absolute values, you get positive 1. That's less than 2. Pick anyone outside of this range. Minus 2. Minus 2 minus 1 is minus 3. Take the absolute values of that. I get positive 3. False. Pick a number over here, like a 4. 4 minus 1 is positive 3. Absolute value of positive 3 is positive 3. 3 less than 2, false. So these guys will not work. Only the middle will work. And had I turned the sign around, I would say from negative infinity to minus 1 and from 3 to infinity, literally the opposite of this would be the answer. So in a weird way, if someone gave me this one, I'd actually solve the other one and just take the opposite, because computationally it's easy. But you'd have to, if you do something like that, you'd have to remember to take the opposite. So I won't really recommend that or write that down, because I don't want to try it and then you forgot and then you told me I could do it. For political reasons, let me not actually write that down, but it's something that could work. Okay, so that's how you solve that. And this is an important thing to know about inequalities involving absolute values. You can break things down like this into that. Yeah, and that's pretty much all you need to know about solving inequalities. Alright? So problems like that come up in domains and stuff like that. So that's 1.8. Let's actually start 1.9. We won't finish it, but let's get it started because a lot of the first part isn't really computational anyway. 1.9, we will talk about three things. The coordinate plane, as it's called. Equations, graphs of equations. We'll talk a little bit about that. And this section ends with talking about the circle. So the coordinate plane refers to the xy plane. This is often referred to as the Cartesian plane. The Cartesian plane is named after René Descartes. So I don't know if any of you are taking philosophy, but Descartes is taking philosophy. Yeah. So the guy I think therefore I am, that guy, the same guy, came up with the xy plane in the 1600s, right? Which was one of those really pivotal events, right? It's one of those things that completely revolutionized it. There's like events like the invention of the number 0 and what that did for mathematics, and then there's the invention of the xy plane and what that did for mathematics. Completely changes how we study it, because now with the xy plane we can now visualize things. So I can see an equation, this is an equation, and I can talk about what that means in a quadratic and its formula. But knowing that this has a picture, right? Knowing that I can think of a picture when looking at an equation it revolutionized mathematics, right? So yeah, this whole xy plane thing that we're used to so much, yeah, no one thought of that until the 1600s. So before that, there were no pictures. Mathematics was just a lot of tedious calculations, and it was kind of a difficult thing to get around. But this guy here, the way we can set up the x and y, this is called the Cartesian plane. And a guy called René Descartes came up with it in the 1600s at some point. I don't remember the exact date, but it was a very important. So when they say Cartesian plane, it's from the last part of his name. Cartesian. Okay. So René Descartes came up with the idea of a Cartesian plane. We call this the coordinate plane because we can plot things inside this plane called coordinates. So by convention, we can plot something called a coordinate on this plane. And it somehow is a pictorial representation of a pair of numbers. So we can talk about something called a coordinate. So you might hear them talk about the Cartesian plane or the coordinate plane, and it's a way to visualize how a pair of numbers relate to each other. So remember, the first number is the x coordinate, the second number is the y coordinate. So I can talk about the first number. We'll talk about this more when we get to functions. Can represent the input that I plug into a function. The second number will represent the output. So I can talk about an input happening here and an output responding here, and I can pictorially represent that on the Cartesian plane by a coordinate. And the idea is, if I look at an equation and I look at all possible coordinates, that results in what we call a graph. A graph is simply a picture of an equation. Which is super helpful. I don't know how many of you have taken psychology or you're interested in neurology or something, but thinking in pictures is a very basic human way to think about things. Analyzing the world through our visual faculties is super important. So if you can get a picture into something, it always works. Right? It always makes it better. It always helps people to understand things more when you can draw a picture about something. So it was a very important idea. I'll talk about the graphs a little bit later. I just want to talk more about individual points in the plane and the relationship they can share between each other. But before that, we want to discuss distances between points. So if I have 2 points in the plane, is there a way that I can measure the distance between these 2 points? And midpoints between 2 points. But first, to derive that, the formula that we're going to use here, we actually need another important fact. Time to go. You have to leave early? Okay, all right. Okay, but first, let's talk about another important fact, and then we'll get to be able to attack these with some sort of sophistication. Consider the thing that we call a right triangle. This is called a right triangle because it has an angle that is 90 degrees. We call this a right angle. A triangle that possesses one of these. A triangle can possess at most one of these, but any triangle that has one, we call it a right triangle. We can talk about the lengths of the sides of this triangle. So let's say I have the length here, this is A, and I can talk about the length here, this is B, and I can talk about the length that's opposite the right angle, call that C. The guy that's opposite the right angle, we call that the hypotenuse of the right triangle. These are called the legs of the triangle. So that's one leg and that's another leg. And the hypotenuse is the longest side. And it is opposite the right angle. Now I'm going to do something that might seem very strange at first. Okay? I'm going to make 4 copies of this triangle, and I'm going to arrange them in this beautiful pattern, but it's an odd pattern because why would anyone do this? But it's also it's a pleasing pattern. Let's say I have one of these guys, and take 4 of these, same triangle, okay? So let's say I have, put one here, that's A and B, that would be C. Turn one to the side and attach it to that tail. That would be A, B, that would be C. Take another copy, flip it around that way. That would be A, B, not drawn to scale, obviously. That would be C. And then take the last one and arrange it that way. So that's A, B, that's C. I've just created a square, you realize? This here, the length is A plus B. This here, the length is A plus B. Now let's consider the elementary fact. I can actually find the area of this square in 2 distinct ways. I can use the general formula for the equation of a square, length times width, A plus B times A plus B. I can also find the area of this square by actually adding up the area of these distinct shapes. Also, I can take 4 times the area of the triangles plus the area of the inner square. Right? Now what's the area of this triangle? Well, it's half base times height, right? So I can say it's half A times B. And what is the area of the inner square? Well, it's a square with all sides are C. So that is just C times C, that's C squared. This of course means that A plus B all squared must be the same as this expression. Let's kind of simplify this a little bit. We're now great at algebra, we know what that is. That's A squared plus 2AB plus B squared. Here, 2 cancels for 2, so that's 2AB plus C squared. I can subtract 2AB from both sides, and I end up with this curious equation. A plus B squared equals C squared. This is a very important result. It is called Pythagoras' theorem. Proven by Pythagoras, another philosopher. That's the name of the theorem. It says for any, and I want you to be aware that it didn't matter what particular right triangle I picked. A, B, C could be anything that I can arrange in this shape. For any right triangle. A, B, C with hypotenuse C, we have A squared plus B squared equals C squared. That expression is called Pythagoras' theorem, and it applies to, well, if the C is here, the A is here, the B is here, or vice versa, it's not going to matter. That is an important result. You are expected to know that result. Okay. You don't need to know how to prove it, but you should know this, right? It's called Pythagoras' theorem. And like I said, this is why pictures are important, because there are some facts that we know about equations. Well, when you see a picture, it's like, yeah, it had to be that. How could it be anything else?
Could you hold off 2 seconds? Sorry, I just wanted to take a quick picture. Right there.
So you don't really need to know this, but you do need to know that. That's in a box. I'm never going to ask you to prove Pythagoras' theorem. It's never going to be a question. I just wanted to emphasize that these rules that we give you in math class, they aren't just made up or fall out of the sky or were given to us by the gods. No. We observe nature, and yeah, this is what it had to be. A right triangle has to behave this way. It couldn't be anything else. Yeah, so that's Pythagoras' theorem. With that, now we can talk about the distance. Now let's talk about what we call the distance formula. So the goal here is to find the distance between 2 points. Now, it will be nice if we can plot a picture, so let's use the Cartesian plane. And let's assume the 2 points I'm talking about are these 2 points. Let's say it's x1, comma y1, and call it x2, comma y2. Now, what I'm concerned with is my green chalk? Oh. What I'm concerned with is this guy. I want to figure out I want the length of this, which is the distance between these 2 points. The shortest distance between 2 points is a straight line. And so usually when you want to measure the distance between 2 things, you're thinking about a straight line distance. The trick here is to recognize that I can kind of create a right triangle. Okay? So I can think of this like the C, which is the hypotenuse. I can think of this length as the A and that as the B. And Pythagoras' theorem will apply, because this applies to every such thing. Now, if we start to worry about what is the length from here to here, well, the x value here was x1, the x value here is x2, the distance here is x2 minus x1. Or you want to find a horizontal distance, the right point minus the left point. Similarly here, if I want to measure the height of this thing, that's going to be y2 minus y1. Right? So if I set my b is equal to this, my a is equal to this, the c is what I want, question mark, I can now develop a formula for that. By Pythagoras' theorem, I know that a squared plus b squared must be equal to c squared. Well, a squared just means x2 minus x1 all squared, plus b squared means y2 minus y1 all squared, and c squared is the distance, that's the d squared. However, if I care about the distance, solving for this would just mean taking the square root. So I end up with the square root of this. This is called the distance formula. This allows us to find the distance between any two coordinates. So the distance formula between x1, y1, and x2, y2. So give me 2 points that I can plot in the plane. I can find the distance between these 2 points by using this formula. It's called a distance formula. In the remaining time, let's see if we can prove the midpoint formula. So next time we'll actually use these in an example. We'll talk about how to go from the distance formula to developing the equation of a circle, and then we'll talk about some information on graphs in general. When we are drawing pictures of equations, some of the things we want to consider. Let's look at the midpoint formula. And so this is our goal here, is to find the middle point on the line connecting two points. So in other words, let's say I have 2 points and the line connecting them. So this is x2, y2. This is x1, y1. I am concerned with finding the point that is smack dab in the middle here, called the midpoint, where it is a point on the line such that the distance here and the distance here are the same. Okay, so these two distances are the same thing. For that we need, so remember a little thing about similar triangles, which I'll just mention. Similar triangles. Triangles are similar if corresponding sides are proportional. The important takeaway, though, is that similar triangles can be created by slicing a given triangle with a line parallel to one of its sides. So that's going way back in geometry. I'm not really going to discuss why that's true. So just know that that is true. And here's how you'd actually think about it. So imagine here, again, we're on the xy plane. We have 2 points, x1, y1, x2, y2. And again, I can kind of create this triangle. Now, what I care about is the midpoint. And how we actually talk about a way to actually find that, that should be a right angle, is to actually just slice this triangle with a vertical line that passes through the midpoint. Now it turns out you will create two similar triangles. It turns out that this blue triangle here is going to be a mini copy of the yellow triangle here. Right? In other words, all the sides will be proportional. Okay? So the thing is, since this distance here is half the entire distance, which is that, it would also immediately mean that this length here would be half the B side, and this length here will be half the A side. Right? Because all sides will be proportional. In other words, this side, we know the length of A is actually x2 it's going to, well, ultimately it's going to become x1 plus x2 all over 2. This one would become y1 plus y2 all over 2. And what you kind of think about for that, how you would get to that is to call this xy, apply the distance formula here, and set the x coordinates equal and the y coordinates equal, and ultimately you'll derive that has to be true. And I mean, we're out of time, so I'll just rush to finish this. So ultimately we get that the midpoint must have x coordinate this and y coordinate this. You don't need to know where it comes from, but you do need to know that. Next time we will do a lot more complication now. These two forms are going to give us a lot of. Okay, I'll see you Monday.